Okay, Algebra 2, this is section 8.3. We're starting to get into the computational stuff for stats. So some of this is going to look familiar, some of it might just look a little different than what you're used to seeing. So the first thing that we're going to talk about is a population mean, and mean is average, which you probably have heard before. So whenever we talk about calculating the average or the mean, we're talking about adding them all together and dividing by the number of numbers there are. So the population mean is the population parameter that calculates the mean or the average of the entire population. And population mean is represented by this little symbol. Here's what it looks like drawn out. It kind of almost looks like a W, but it's a cursive U, and that's pronounced mu. It's kind of a weird thing, but that's what we use to talk about average. The second one is a population proportion. So they might say what proportion of your data is, below 30, or what proportion of your data is above 90 or whatever. So you're looking at a percentage or a decimal. Okay, so population proportions are going to be decimals that are between 0 and 1, or their percentages between 0 and 100. Okay, is how you're going to represent proportion. So if you represent them as decimals, which is usually how proportions are represented, they're a decimal between 0 and 1. So like 0.6 would be the equivalent. 0.6 would be the equivalent of 60%. So it's just whatever way you prefer to write it in. Most of the time your book is going to give it to you in decimals, but you can write it as 60% also. It doesn't make any difference. So they give you an example down here of population mean and population proportion, and they say that the student has a test scores of 100, 100, 91, 84, and 75. That's 5 total test scores, and they want us to find the average. Okay, they use this little symbol right here, which we don't emphasize a whole lot in Algebra 2, but they use this a lot in statistics. This guy means the sum. That little E means the sum. So basically this is saying just take all of your x's, all of your values, and add them together. So we're going to add, down here they have it written, we're going to add 100, 100, 91, 84, and 75. You add them all together and you divide by the number of numbers there are. So there's 5 numbers. Those added together was 450 divided by 5, so my average is 90. Okay. Then they hop over here to population proportion, and they say the fraction or percent of the sample. They're interested in finding the proportion of tests higher than 90. Okay, so I'm looking at higher than 90. 75 is not higher than 90. 84 is not higher than 90. 91 is higher than 90, 100, and 100. That's 3 test scores out of 5 that are higher than 90, which as a decimal is 0.6, or 60%. I used a really good example up here. So 0.6 or 60%, most of the time your proportions are going to be a decimal. But again, you can put them as percentages if it helps you to think about it that way. Okay. Now, using data to estimate a population mean, they give us this table of information, and they're saying that residents of a dorm, there's 51 residents. So if we're looking at this table, number of residents here, these all should add up to be 51. Okay. They were surveyed to see how many classes they are taking this semester. So 6 students are taking 1 class, 5 students are taking 2 classes, there's 3 students taking 5 classes, etc., etc. So we want to find the population mean. Okay. I'm going to write this information up here. Don't write this down yet. Because I'm going to show you an easier way of doing this. But what this is saying right here is that 6 students are taking 1 class. Then I have 1 class plus 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 1 class. Again, don't write this down because I'm going to show you an easier way of doing this. Okay, that's 6 students taking 1 class. Right? If there are 5 students taking 2 classes, 1, 2, 3, 4, 5. There's 5 students taking 2 classes. And then I would do the same thing for 26 threes. I would add 26 threes in there and add 11 fours in there and add 3 fives in there. And then at the end, I'd keep doing that, at the end I would divide that all by 51. okay? But I don't want to have to write out 3 26 times or 4 11 times, okay? So what this is essentially saying is that if 6 people are taking one class, that's kind of like 6 times 1. There are 6 ones up here, okay? If 5 people are taking 2 classes, I'm going to add that to 5 people taking 2 classes, okay? If there are 26 people taking 3 classes, I'm going to do 26 times 3 because that would be 26 threes all written out. If there are 11 people taking 4 classes, I take 11 times 4. And if there are 3 people taking 5 classes, I do 3 times 5. This basically is like what this is doing, except I don't have to write out the number 3 26 times or the number 4 11 times, okay? And I divide that all, just like I would up here, by 51. So go ahead and do write this one down, but don't write this one down because this is essentially what this means. I mean, you're more than welcome to write it down if you want to, but this is what this means, but this is the shorter version of doing that, okay? So 6 times 1, I'm going to write out all the steps. If you want to just plug this into your calculator and have it do it, you're more than welcome to. So 6 times 1 is 6, 5 times 2 is 10, 26 times 3 is 81, 78, plus 44, plus 15, all divided by 51. Okay, I'll do this in my calculator right quick. 6 plus 10 plus 78 plus 44 plus 15 is 153 divided by 51. Okay. Now, before I give you the answer to this, we're trying to figure out what the average number of classes there are. Okay. So the average number of classes is probably going to be a number between 1 and 5 because those are the only numbers that I'm given. Okay. And most of the people have 3 classes. So 26 people have 3 classes. So I'm going to guess the average is going to be really, really close to 3. Okay, because the most people have that many classes. So let's see, 153 divided by 51 is exactly 3. Most of the time it will come out as a decimal when you do that, but this one did not for some reason. So the average number of classes is 3, just by looking at this information. Okay, there we go. All right, next example. This is a proportion one, and this one goes by really quick. In a population of 250 people, okay, 90 say they prefer running over hiking. So we have 90 runners over 250 total. What is the proportion of people who prefer running over hiking? When you do that, you just put the runners over the total, 90 over 250, and we write that as a decimal, 90 divided by 250. If you don't want to type as much into your calculator, you can lump off one of those zeros and just do 9 over 25. That as a decimal comes out to 0.36. So 0.36 is the proportion of people who prefer running over hiking. Okay, what percent of the population prefers running to hiking? That would be 36%. If I convert this decimal to a percentage, I just move this decimal 2 places, and it is 36%. Okay, pretty easy. Now we talk about margin of error is the last thing. Okay, because this information up here has to do with a sample of people. We're only sampling 250 people. This we're trying to estimate as a population. So we're trying to say these 250 people are an accurate representation of what more than 250 people would be, of an entire population of runners and hikers, okay? But in that, there comes some margin of error. So I can't say 36% of everybody in the world prefers running over hiking, okay? But according to my sample, 36% does, okay? So in my population, it won't necessarily be exactly 36% because there is some margin of error that occurs, okay? 36 is only an approximation based upon what the results were of my sample. So the accuracy of a sample survey is based on 2 key factors. One of them is the margin of error, and the other one is the confidence level. Okay, we're not going to talk about confidence level yet today. We're just going to talk about margin of error. So margin of error is how far off your answer is. Okay, so 36%. How far off is that from what the actual could be? Okay, so margin of error is just how good of an approximation is 36%, basically. Okay, to calculate margin of error, in statistics, it's a little bit more of a complicated formula, but for margin of error for you guys, it's just going to be positive and negative 1 over the square root of n, and n is the sample size. Okay, so here 250 was our sample size, all right? And then you multiply that by 100, okay? So we're going to calculate the margin of error down here in example 3. A survey is conducted to determine how many people will vote for the school presidential candidate. The results of the 500 students, I'm going to write that down. 500 is my sample size, so 500 is equal to n. Students surveyed showed that 62% will vote for candidate B, whoever that is. So our results say 62%, kind of like up here our results said 36%. So we're trying to determine how far off is 62%, okay? 62% was just based upon a sample, but if I'm talking about the entire population voting, will 62% of the entire population actually vote for candidate B? Probably not, but it might be close to 62%. Okay, so we need to figure out how far off that number is. So our margin of error is plus and minus 1 over the square root of n is 500, and we're going to multiply that by 100. Okay, 1 over the square root of 500, 1 divided by square root 500 is, let me write it over here, is plus and minus 0.0447, I'm going to say. 0.0447, okay? And I want to multiply that by 100. I haven't done that yet. This part was just the 0.0447, okay? If I multiply that by 100, you just move the decimal 2 places. So I have positive and negative 4.47%, okay? So that means that this number here that I got as my result could be off by almost 4.5%. So according to my sample, 62% of the people voted for the candidate B. But in real life, when I actually do the population, if I take and add 62 plus 4.47, 66.47%, or if I subtract that, 57.53%. Anywhere between 57.53% and 66.47% are actually going to vote for candidate B. So this is what my sample gave me, but this is what my population is going to yield. Somewhere between 57 and 66.5% are going to be voting for candidate B. Now, the margin of error gets smaller. This percentage right here, the amount of error that I have gets smaller the larger my sample is. So if I would sample 1,000 people, I would have a smaller error. Well, if I want my error to be as small as possible, why don't I just sample a whole bunch of people? Well, because it's not always cost effective, and I'm not always able to access that many people to ask them whether they're going to vote for candidate B or not. So I want my sample to be as large as possible, so this number is as small as possible, but that's not always, I can't always do that, all right? So in example 4, they're giving us a margin of error. They're saying, hey, my margin of error, I want my margin to be 3%. I want it to be smaller than this 4%. How many people do I have to sample in order to get 3%? Okay, now 3% is less than 4.47, which means I'm going to have a sample that's larger than 500. But we can figure out how many people exactly I have to sample in order for my margin to be that small. So you're a member of a research team and are going to run a simulation. The simulation needs a result in an adequate sample size and margin of error for each trial. Find the sample size you need to use for your simulation for a margin of error that's 3%. I want my margin of error to be small. So I need to figure out what sample size I need. So I'm going to just do positive and negative 3 is equal to, and I'm going to set it equal to this formula up here. My margin of error was plus and minus 3. I want that equal to positive and negative 1 over the square root of n times 100. Okay, so this is my equation. I just set that equal to plus and minus 3, and then I just manipulate this equation a little bit, okay? Positive and negative 3, since it's on both sides, I'm just going to cancel those out because they really don't matter in this case. So I just can deal with 3 equals 1 over the square root of n times 100, okay? Then I've got to decide in my order of operations what I'm going to do next. So this 100 over here, I can divide both sides by 100. That's going to be my next step. 3 divided by 100 is kind of like moving the decimal the opposite direction. So 3 divided by 100, you can do it in your calculator, or you can just mentally think the decimals here, move it 2 places. 0.03 is equal to 1 over the square root of n. Okay. Then to get that square root of n out of there, I'm going to multiply by the square root of n, multiply by the square root of n. So I have the square root of n times 0.03 is equal to 1. Okay, I'm almost done. I'm almost there. I want to get that square root of n by itself, so I'm going to divide by 0.03, divide by 0.03. The square root of n is equal to 1 divided by 0.03 is 33.333. Okay, and then to get rid of that square root, I square both sides. So if I take this number and square it, n is going to be equal to 111, or 1,111. And this is what my sample size would have to be in order to have an error that's as small as 3. Okay. Part B, they're saying, well, what if I don't care about having a large error? What if my error is 10? Okay. Now think about what that's going to do to your sample size. If I don't care about my error, if my error can be as large as it wants to be, or as large as 10, I could probably do a pretty small sample size. Okay, the smaller your sample size, the more inaccurate your data is. Okay, so if I want my data to be, it can be inaccurate if it wants to, then I can do a smaller sample size. So I'm going to set this up exactly the same. Positive and negative 10 equals positive and negative 1 over the square root of n times 100. And then I lump off the plus and minuses. Okay, next step, I divide by that 100. Divide by 100, divide by 100. So I have 1 over the square root of n on this side equals 10 divided by 100. I move the decimal 2 places, so that is 0.1. Okay, I'm going to multiply both sides by the square root of n. Multiply by the square root of n. So I have the square root of n times 0.1 equals 1. And then I can do 0.1 divided by. So I have the square root of n equals 1 divided by 0.1. And 1 divided by 0.1 is 10. I should have known that. I don't know why I did that. 10. And then to get rid of that square root, I square both sides. And 10 squared is 100. So my sample size just needs to be 100 if I don't care that my error is as large as 10%. Okay? If I want a small error of 3%, I would need a sample size of 1,000. Okay? So the smaller my error, the larger my sample needs to be. The larger my error, the smaller my sample needs to be, or can be. So there you go. That's a little bit on the computational parts of statistics, and that's it.